Pluto's orbit has recently raised intrigue and speculation among scientists and space enthusiasts alike. Once considered the ninth planet in our solar system, Pluto was reclassified as a dwarf planet due to its unusual orbit. Despite this demotion, Pluto's influence in our cosmic neighborhood is undeniable, stirring up interest about its potential interactions with nearby planets, especially Neptune. Renowned figures like Neil deGrasse Tyson and Michio Kaku have commented on the possible implications of Pluto's orbit, hinting at a rare event that may have profound effects on Earth. Pluto's orbit is particularly captivating because it periodically crosses Neptune's orbit. However, due to their precise gravitational dance, the two bodies never collide. This phenomenon, which has been a source of fascination since Pluto's discovery in 1930, involves complex gravitational interactions that prevent Pluto from intersecting directly with Neptune's path despite their overlapping orbits. Pluto's orbit deviates from the typical circular paths of other planets, taking on an elongated, oval shape. At certain points, Pluto's distance from the Sun varies dramatically, sometimes closer than Neptune, at other times much farther away. Additionally, Pluto's orbit is tilted by 17 degrees relative to the orbital plane of the larger planets, adding another layer of complexity. The gravitational interplay between Pluto and Neptune helps maintain a stable but intricate orbital pattern known as libration. For about 20 years during each orbit, Pluto ventures closer to the Sun than Neptune, creating a periodic convergence that avoids collision due to precise gravitational synchronization. Scientists use advanced simulations to analyze this pattern, which highlights how the gravitational forces of Neptune and the Sun guide Pluto's orbit, ensuring a consistent separation between them despite their close encounters. Computer simulations, particularly in the late 1990s, helped astronomers understand the long-term stability of Pluto's orbit. These models showed that even minor changes in Pluto's position or velocity could potentially alter its path dramatically. However, Pluto's orbit has remained stable over billions of years, suggesting that certain gravitational principles act as safeguards against chaotic changes. These principles prevent Pluto from colliding with Neptune and maintain its unique orbital path within the solar system. Understanding Pluto's trajectory has been instrumental in shedding light on the dynamic mechanics of our solar system. Even as Pluto crosses Neptune's orbit, their separation remains significant, minimizing the risk of an actual collision. This precise balance, facilitated by gravitational interactions and the VSOP, variations séculaires de orbites planétaires, calculations, demonstrates the delicate cosmic choreography that governs planetary motion. Despite the inherent chaos in space, the predictable patterns within Pluto's orbit underline the stability of our solar system's dynamics. While Pluto's unique path may appear erratic, it adheres to an underlying pattern that ensures consistency over time. Astronomers continue to monitor Pluto's interactions, using simulations to explore potential future scenarios. While the long-term predictions of planetary orbits can be challenging, these models help us understand the potential outcomes while acknowledging the limits of our predictive capabilities. Planets, including the gravitational dance between Pluto and Neptune, are grounded in fundamental principles of physics. Michio Kaku's work in theoretical physics, particularly in string theory, aims to unravel these principles at their core. He suggests that exploring complex celestial mechanics, such as Pluto's orbit, can yield insights into the foundational laws of the universe. Like Neil deGrasse Tyson, Kaku has considered the potential collision of celestial bodies and connected it to his theories about the universe. A collision between Pluto and Neptune, while significant in astronomical terms, could provide a unique observational opportunity, potentially contributing to our understanding of string theory and other areas of theoretical physics. Such an event could generate extreme conditions of energy and gravity, shedding light on the behavior of fundamental particles and forces under intense circumstances, a critical concept in string theory. Additionally, the gravitational waves produced by such an occurrence could offer valuable data for testing string theory's predictions about gravity and spacetime. While the direct impact on Earth would be minimal due to the distance from these outer planets, the scientific implications could be profound. Understanding events like this could enhance our knowledge of the fundamental nature of the universe as depicted by string theory and other areas of theoretical physics. Pluto's distinct characteristics, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. However, the universe still holds many mysteries, and the three-body problem is one of them. Researchers anticipate other possible interactions, underscoring the ongoing quest for knowledge and exploration in the vast universe. Although highly unlikely, there remains a small chance of planetary collisions in space, as a planet's orbit is influenced by various factors, such as the gravitational pull from other planets. Scientists refer to this as the three-body problem in systems like the TRAPPIST-1 system, which contains 7 Earth-sized planets. In such systems, gravitational forces create a type of rhythm in the planet's movements, known as orbital resonances. Over time, these orbits can make a planet's path less stable and might lead to collisions, even though crashes are not currently occurring in systems like TRAPPIST-1. Scientists continue monitoring these systems to understand how planets affect each other's orbits, especially when they are in close proximity, which helps in understanding planetary motion in space. This text, while technical and detailed, covers many topics related to Pluto's orbit, gravitational effects, and potential collisions with Neptune, all within the context of planetary dynamics and theoretical physics. Delving into the complexities of Pluto's orbit and its interactions with Neptune and other celestial bodies reveals that our solar system's dynamics are far from static. Pluto, once thought of as a solitary wanderer in the outer reaches, now emerges as part of a complex gravitational dance spanning billions of kilometers and millions of years. The gravitational forces exerted by Neptune, the 8th planet from the Sun, play a crucial role in shaping Pluto's orbit. Despite their great distance, these two celestial bodies occasionally come close due to the eccentricity of Pluto's orbit. This eccentricity means that Pluto's orbit is not a perfect circle, like those of the inner planets, but rather elliptical in shape. This characteristic leads to significant variations in Pluto's distance from the Sun throughout its approximately 248-year orbit. At its closest approach to the Sun, or perihelion, Pluto ventures inside Neptune's orbit, coming within about 30 astronomical units, AU, of the Sun, closer than Neptune's average distance of roughly 30.1 Australian dollars. However, at its farthest point from the Sun, or aphelion, Pluto travels over 49 Australian dollars, far beyond Neptune's orbit. These distances mean that Pluto and Neptune's paths intersect at certain points in their respective orbits. The gravitational interaction between Pluto and Neptune is particularly fascinating because it illustrates the delicate balance of forces in our solar system. While Neptune is far more massive than Pluto, its gravitational impact on Pluto is still substantial due to their occasional close encounters. These encounters can subtly alter Pluto's trajectory over time as gravitational perturbations from Neptune influence Pluto's orbit and shape its path around the Sun. Additionally, Pluto's orbital plane is tilted at an angle of about 17 degrees relative to the ecliptic plane, the plane in which most planets orbit the Sun. This inclination adds another layer of complexity to Pluto's orbit, as it means Pluto's path through space is not perfectly aligned with those of the major planets such as Mercury, Venus, Earth, Mars, Jupiter,
Understanding
Saturn,
the
Uranus,
orbit of
and
Pluto
Neptune helps us gain insights into the complex workings of our solar system. Pluto's orbit shows us how seemingly unpredictable paths can be influenced by gravity, illustrating the intricate ways objects move in space. Studying these phenomena is essential, as it deepens our knowledge of our place in the universe. When we examine space, we notice that celestial bodies can behave in surprising ways, and Pluto's orbit is an excellent example of this instability. Unlike the nearly circular orbits of other planets, Pluto's orbit is more elliptical, which means it is not a perfect circle. At certain times, it even travels closer to the Sun than Neptune does, adding an element of excitement as Neptune also moves along its orbit. Despite the slim possibility that Pluto and Neptune might come close to each other one day, Pluto's unusual orbit demonstrates how gravity can act as an invisible force, pulling objects toward one another while keeping them in balance. Even though Pluto and Neptune may appear to be on a collision course, their orbits are carefully structured due to the gravitational pull that guides them. Pluto's orbit teaches us that space is full of surprises. What initially seems chaotic can be a delicate balance of forces. By studying Pluto's path, researchers gain valuable insights into the complex mechanics of our solar system. This ongoing observation and research are essential for expanding our understanding of the universe and our role within it. If Pluto and Neptune were ever to collide, it would be a monumental event, significantly impacting our understanding of the solar system. While we've made strides in studying space, much remains unknown. Understanding the dynamics of Pluto's orbit offers critical insights into how our entire planetary system functions, revealing how the positions and movements of planets can affect the trajectories of other celestial objects. Despite the complexities of space, some experts have expressed concerns about the possibility of Pluto colliding with Neptune. This raises questions about how such an event might occur, even though it remains unlikely. Renowned astrophysicist Neil deGrasse Tyson has shown a keen interest in Pluto. He views the decision to classify Pluto as a dwarf planet rather than a major one like Earth as progress in our understanding. Tyson believes we are continuously learning new information about how objects move through space. To him, Pluto's unusual orbit serves as a reminder of how much remains undiscovered. Tyson finds the mysteries of space fascinating and recognizes that significant events like the reclassification of Pluto engage people's interest in astronomy. He hopes to help others stay intrigued by the captivating and sometimes unusual aspects of space science. Tyson collaborates with other researchers to raise awareness about the potential risks associated with Pluto's erratic orbit, emphasizing the remote possibility of a future collision between Pluto and Neptune and the potential impact it could have on our solar system. An impact between Pluto and Neptune would be an extraordinary event, possibly releasing massive energy and even breaking Pluto into fragments. Debris from the collision could spread across space, potentially impacting other planets and moons. Neptune's orbit could also be affected by the collision, altering its path. Noted theoretical physicist Michio Kaku, known for his contributions to string theory and advancements in technology, has also shared his perspective on space exploration. Kaku believes that understanding celestial mechanics and theoretical physics can provide a deeper comprehension of space travel's future. He sees Pluto's orbit as a window into the future of space exploration. By examining the gravitational interactions and orbital dynamics of bodies like Pluto, we can improve future space missions, ensuring safer navigation within the solar system, foreseeing potential dangers, and planning expeditions to new regions of the cosmos. Kaku emphasizes that lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, offering a guide for venturing into distant worlds. He often highlights the deep connection between celestial mechanics and theoretical physics, stressing that the interactions of